Welcome back to DB STEM Tutoring. Today, we will be talking about electronegativity, one of the fundamentals of chemistry and biology. So, we can first start off with a basic definition of electronegativity, which is that electronegativity is the tendency for an atom to attract shared electrons when forming a chemical bond. Now, this can be a wordful at first, but in this video, we're going to talk about it and make sure that you understand in the end what this means. So in order to fully understand this, we need to first look at what causes differences in electronegativity in different atoms. So the periodic table is shown below, but instead of the mass numbers and atomic numbers of the elements, instead the electronegativity values are depicted for each element. For right now, in basic chemistry or biology, we only need to worry about two factors that can affect electronegativity. One is nuclear charge and the other atomic radius. So let's look at nuclear charge first. As most of you should know, each atom on the periodic table follows the octet rule, although there are a few exceptions. The octet rule basically says that each different atom will strive to have a full octet, which is 8 electrons, unless you're on the first row, because the outer shell can only fit 2 electrons. So each element starts out with a set number of electrons. As you can see, the first column starts out with 1. The second column starts out with 2, and etc. In basic chemistry, for right now, you can ignore the transition metals, which are these elements in the middle right there. So for right now, you can just ignore those. So this would be the third column, 4th, 5th, 6th, 7th, and 8th. The 8th column are called noble gases. Those have 0 electronegativity, except for maybe some of those at the bottom, because they have full octets, so they don't want any more electrons. So they have 0 electronegativity. So, as you can see in the trend, as you increase in the number of electrons in the outer shell, the electronegativity values will start to increase, because as you get more electrons in the outer shell, the more likely the atom will want to get all of its shell filled. So as you move from left to right on the periodic table, let's see here, as you move from left to right, which is like that, you will increase in electronegativity, because the atoms on the right, with 7 especially, will really want to fill that octet shell because they only have 1 electron left. So they'll really be very electronegative. Now, the second factor for electronegativity would be the atomic radius of the atom. So the atomic radius, in a nutshell, is basically just how far away the outer shell is from the nucleus. As you go down the rows on the periodic table, let's use a different color. So as you go down, as you go down the row, the atomic radius will increase, because you just keep adding shells. The first row has 1 shell, the second row has 2 shells, the third row has 3 shells, and etc. So for each row, the atomic radius will keep increasing. So this increase in atomic radius of the atom will decrease the effective charge of the nucleus, because as outer electrons get farther and farther away from the nucleus has less and less of a pull on them. Thus, because of this, the electronegativity will decrease as you go down the table. So let's not put it pointing that way. Let's point it this way. The way it's pointing basically means the more electronegative the atom is. So from this graph, using these trends, you can determine what is the least electronegative atom along with the most electronegative atom, and everything in between. You can compare electronegativities among different atoms. And one of the most important atoms on this periodic table would be fluorine, because it is the most electronegative atom out of all of the atoms on the periodic table. Now, after talking about the factors of electronegativity, we can talk about the types of bonds that are affected by electronegativity. So let's move down. So if you don't know what a bond is basically just a connection between two different atoms, or two same atoms. It's just a very simplified way to put it. So in chemistry, there are two types of bonds: polar and nonpolar. So polar bonds, so polar and nonpolar. So polar bonds are just bonds between two atoms in which the electronegativity of the two atoms is greater than 0.5, the E value. And in nonpolar bonds, it's just the opposite. It's less than 0.5. So this is the number you need to remember if you want to talk about polar or nonpolar bonds. Now let's put this into practice. Let's talk about an example of this. So you can find the difference between electronegativities of the two atoms in a bond by just subtracting their electronegativities. Like each atom will have different electronegativities. Like oxygen has 3.5. If it's bonded to like a carbon, its value of 3.5 would be subtracted from 2.5. Its difference is 1. So that would be a polar bond if they were connected. So let's look at an example. So let's use hydrofluoric acid. In this case, you don't need to remember the name, but hydrofluoric acid is basically just this: a hydrogen bonded with a fluorine. Okay, so this is the bond as shown by the single line connecting the two. But this entire molecule is just two atoms of hydrogen and fluorine. These two atoms are bonded together with a single bond, and from this we can determine what kind of bond and the chemical environment that this bond creates between the hydrogen and fluorine. So you can pause the video here and try to determine yourself if this is a polar or a nonpolar bond. So if you pause the video, I can show you the solution. So we can determine if this is a nonpolar or polar bond by determining if the electronegativity between hydrogen and fluorine differs by less than or more than 0.5. In this case, the electronegativity of value for fluorine is 4.0, and the electronegativity value for hydrogen is 2.1 for hydrogen and fluorine. Now, we can find the difference between the two by merely just subtracting 4.0 from 2.1, and you get, 1.9? Now, 1.9 is definitely greater than 0.5. This means that the bond between the hydrogen and fluorine in this case is polar. So this is a polar bond, and if you got this right, good job. If you didn't, you can try again. So now that we know that the bond is polar, we can talk about what this polar bond really means for the entire chemical nature of this molecule. When a molecule has a non-polar bond, a polar bond, not non-polar. When they contain a polar bond, they are said to contain a dipole. So let's look at this. So this is the same molecule, hydrogen and fluorine connected by a single bond. This is what we call electron density graph. So blue means lack of electrons and red means more electrons. So the line with the weird symbols on top is what we call a dipole moment, which is basically just a partial charge. This is because an atom that has a greater electronegativity value than the other atom in a bond want to pull the electrons more to themselves, resulting in them hogging all of the electrons in the bond, because the bond right here is composed of, they're sharing electrons basically. They both contribute one electron, then they share it. But electronegative atom or more electronegative atom will want to, they don't share equally, so they'll end up with more of the electron density on their side, which causes a negative partial charge. That's why that's a negative there and that's a positive. So that's a positive partial charge. And that on the fluorine side, that's a negative partial charge. So that's the key takeaway of a polar bond. In a nonpolar bond, you wouldn't see that dipole moment because its bond is mostly even, and the electrons in the bond are distributed evenly, so there would be no difference in electron density between the two elements. There are special cases in which that if a molecule has more than just one polar bond, that doesn't mean the entire molecule is polar. In this case, we only have one bond, and the dipole moment, which is that arrow, shows that there is a partial positive charge to the fluorine. That entire molecule is polar because its dipole moment is like a vector pointing to a specific direction. Now I'm going to show you another example in which there are polar bonds, but the entire molecule is nonpolar. Now let's take a look at the phenomenon where if you have polar bonds, but the molecule isn't entirely polar. So in this case, we're going to use carbon tetrachloride. So carbon tetrachloride is just one carbon and 4 chlorines attached to the carbon. As you see here, the bonds between the chlorine and the carbon are polar because, well, carbon and chlorine have very different electronegativities that are greater than 0.5. You don't need to know the exact, just know that they are polar bonds. So if each one's polar, because there are 4 bonds, then you can draw the dipole movement. So let's use a different color. So let's make it red. This is the dipole moment for each one. As you can see, the carbon keeps getting the positive ones, and each chlorine will get the negative ones. Because the chlorines will all draw the electrons out themselves because they hog all of the electrons. So they, or at least they don't hog all of them, they just have more electron density because they attract more of them. So this is the end. This is the ending. If you draw out all the dipole moments, as you can see, there are 4 total polar bonds. The thing is, this molecule is not polar. This is because these moments, they cancel out. As you can see, this is just like solving a vector. If you're pointing to a not a net position, that means it's 0. So if you put them together, this one, this one, this one, and this one is basically all it comes down to. Now, this isn't the exact geometry of carbon tetrachloride, but that's the entire molecule is symmetrical. So this is in the end how it's going to play out. So these will all cancel each other. Look at this. That cancels with that one, and that cancels with this one. So this is a non-polar molecule. This is just an example of a nonpolar molecule. There's a lot of them. Like carbon dioxide is another one you can talk about. But there's a lot of molecules with polar bonds that are nonpolar molecules in general. This is just a specialized me talking about electronegativity. But in the end, you should get the overall gist of electronegativity. So we can go back to the entire definition of electronegativity. So in conclusion, electronegativity is just the tendency for atoms in a bond to pull on the electrons in the bond because each bond contains 2 electrons from each atom. But because the electronegativity of two atoms could be different depending on what the atoms are, if the electronegativities of one atom is greater than 0.5 of another one, that is a polar bond. If it's less than 0.5 for each of them, then that's a nonpolar bond. So, and having polar or nonpolar bonds could affect the chemical nature of your entire molecule. This is why understanding electronegativity is so important, and especially biology. Chemistry is also really important, but to understand how life works, electronegativity is a very big part of that. So you need to understand what causes electronegativity, which makes it easier to understand the effects of electronegativity. So electronegativity will cause partial charges, will affect the chemical nature of the entire molecule.
Don't forget to like and subscribe to the channel. If you have any requests or video ideas, feel free to comment down in the section below, or you can contact us via our email address provided by our YouTube channel. Hope you enjoyed the video.